I wish there was a way to have that not be quite so loud. So, you know, it's always kind of fun to do a magic trick. So let's do a magic trick to motivate our discussion today. Here's Onyx, and I took the liberty of loading this and fitting a one-factor model to the data. And these loadings are not surprising, but I'm going to do something a little bit odd. I'm going to come over here to this first loading and come down to the starting value part. And instead of having the starting value be 1.0, I'm going to have the starting value be -1. Well, look what happened. Rather than having 4 numbers that were all positive, I have 4 numbers here for loadings that are all negative numbers. Is that a problem? So by the tracing rules, we can think about whether that's a problem or not. So before, the loading was 5.48, now it's -5.48. Is the variance any different? Well, the variance of the first time of measurement is -5.48 times 1 times -5.48. I'm going to get a positive number. It's going to be the same thing. Similarly, the covariance is going to be -5.48 times 1 times -6.63. So that model also predicts a positive covariance between these things. Well, how is it that my computer program came up with one set of numbers with one starting value and another set of numbers for another set of starting values? This has to do with how the computer program is solving the model. So to talk a little bit from Anne's earlier question, we have here a parsimonious model. I have 8 parameters, 4 errors, 4 loadings, and I have 10 elements of the variance covariance matrix. And that means that I'm explaining a lot of things in the data with just a small set of numbers. But what's going on here is the way that the computer program is arriving at a set of numbers depends critically on where we start. So if we come back and change this to the number 1 again, we'll see everything reverts back to positive numbers. And so this issue of how it is that the computer program arrives at numbers is why it's important for you, why you can't just say, I'm going to accept whatever this software does.
New studies available on Prolific
is reasonable. I'm going to get out of that. So let's come back now and consider where we are in the handout. For organization, what I'm going to do is to present to you an idea for the iterative way that these computer programs solve answers. And the easiest way to start out with that is to explain to you something called least squares, or otherwise known as ordinary least squares estimation. And given that that's graphically kind of a nice way of looking at things, we can also come in and then go to maximum likelihood and generalize least squares and explain why those estimation techniques might be preferable to least squares. So to begin, it helps to start with a really small example. So let's just look at 3 little variables, how much people drink on Thursday, Friday, and Saturday. And here's what the data looks like. And if I think about this as a 3-indicator factor model, and I hit the run button, these are going to be the numbers that I look at. And the discrepancy between what the actual correlations are and the correlations predicted by my model is known as a loss function. And for the case of least squares loss, it's pretty easy to understand. This is a standardized solution So any particular guess for numbers can be calculated in terms of error by the following formula. So I will take the correlation in my data minus the predicted correlation based on my diagram. So in this example, 54.54 times 1 times 0.79. And I'll square that number and add it up and across all of the correlations in my model. And that's going to represent a degree of how bad the guesses were for a particular loading. And if you do that across a whole variety of guesses for the factor loadings, you'll get the following picture. So for example, if I start out my model by saying that maybe the standardized loading is for the first factor loading is 0.2, and a guess for the factor loading for the second loading is 0.2, that's going to give me a really high value of loss, a really bad guess about what those loadings are. And what you want to get to is wherever you started your guess at, you want to arrive at this point down here where the guesses for the factor loadings, factor loading 1 and factor loading 2, are at a minimum. Does that make sense? I realize that I'm going through a diagram and a data set and a loss function. But that's basically what I want to start with. So if we're doing this for our factor loadings, I'm going to come upstairs and, when you're looking at your factor loadings, your particular software is going to start out with some starting values for the loadings, and it's going to then iterate until it arrives at this minimum. And that's what it's doing. And whether your computer program can successfully navigate to that minimum or not is something that you need to be aware of or investigate before you start believing the family of numbers that you see in a program. So in this example, given that every loading is part of a product for correlation coefficients, we might consider the average square root of the correlations as an initial guess. So what we're doing here is, to get some start values, I'm taking the observed correlation of variable 1 with variable 2 and variable 1 with variable 3, and taking the square root of that, adding them together and dividing by 2. And that gives me these three numbers. And those are my start values. And for those start values, I can plug that in. In other words, if loading 1 is 0.6495 and 7191, that's going to appear over here. The actual correlation was this. And the least squares loss then is the sum of the squares of the actual correlations minus the predicted correlations summed over all of the loadings in the model. And this leads us to say, well, that's one guess, but how can we change our initial estimates so we get to a better answer? And the way that we're doing this uses something called Newton's method, or the Newton-Raphson method. And some of you have had calculus as much as you want to admit that maybe you didn't, and some of you have never had calculus, and so the notation's kind of weird and you don't know what it is. So what I want to do here is to say to you conceptually what is going on with the Newton-Raphson approach, because it tells you a little bit about how those answers get arrived at. So inside of calculus, there are these things called derivatives. And it's an estimate of slope associated with the given data point. And the easiest way to understand that is to come back to our picture above and say, every possible combination of loadings, if I plotted out all of them and calculated the least squares loss function, is going to look like this. And if I had a marble and I put it on this surface, there are some places where, that marble is going to zoom on out. The slope is going to be very steep at some points. And at other points on this surface, that marble is not going to be moving very fast at all. Like when I'm close to the minimum value here, that marble isn't going to move much. And that slope issue with respect to how much you're sliding on this axis or how much you're sliding on that axis is called a partial derivative. And what we're doing here is saying my new guess for a parameter, theta, and theta is just going to be a vector of all of my loadings, is equal to my old guess, the initial start value I had the first time, minus these derivatives. And these derivatives are accomplishing nothing more than calculating a derivative with respect to the thetas. And that's all really you need to know, in terms of conceptually what a derivative is doing. And the other thing that you can take a look at here is, hey, we've got d theta, inverse, and then this d theta. This little part here gets repeated here twice. Whenever I take an inverse, I'm dividing. Now, just for fun, given that terms get slung around quite a bit, this is a matrix of second derivatives. It has a name. It's called the Hessian. Sometimes when you're computer programming, you're running your SEM software, it will say things like, oh, the Hessian cannot be calculated, as an indicator that your model is not identified. But x prime x inverse x prime kind of bears a resemblance to this part of the formula. So if we're looking at the derivative, this is exactly how you would calculate it. So again, I have my loss function, observed correlations minus the correlations predicted based on a particular set of values, times d delta d theta 1, and this gives me an estimate of the slope. And upstairs, calculating that by hand, this is going to result in a new guess for what this partial derivative is. And that's basically all there is to it. You can follow the equations. Doing that for all of the values gives me this set of values here. The matrix of second derivatives is a matrix of the derivatives of the derivative. So it's kind of not only the slope, but how fast the slope is changing. And I mentioned that that's the Hessian. And that's looking like this. So to get a new set of parameter estimates, we're going to take our old set of loss functions, calculate the second derivatives, and then use that formula to give ourselves a new estimate. So conceptually what's going on, these are the three numbers that we started out by taking the square roots of the correlation and averaging them. And this becomes my inverse of the Hessian and my first derivatives, and that's going to give me a new set of numbers. So whereas I started with these three values, after doing this calculation, I'm going to end up with these values. And then what I do is I take these three values and I apply the formula again. I take these values, I take these values down here and paste them up here and recalculate the derivatives. And I keep doing that until the program stops. It says the game isn't worth the candle. I'm going to call this final set of loadings the answers. So if you've been kind of hitting the snooze button on, here's all of, all this talk of calculus, what is going on here is, here's my initial estimate. After applying the formula that we just talked about above, we got exactly these answers. And applying it again and again and again, our answers keep changing. Every time our answers keep changing, we get a squared loss that gets smaller and smaller. So my first guess was kind of a bad one, but after improving that estimate, the loss function keeps going down and down and down. And after a while, given the wonders of computers, these numbers change very, very little. So at the end, notice by the end of iteration 14, these numbers are changing out in the 1,000, 10,000, 100,000ths place from what they were before. And we then say, well, stop the program. I mean, we're going to take these three values as our guesses about the loadings. So are there questions and reactions to this? Yes, Andreas.
When what is the case when the quite far from when is the case where the FLS number is quite far from the real data?
Well, we're going to at the end of the day, this is my loss function, and my loss function isn't changing much anymore. This is 10 times e to the minus 11th power, so it's a number that's really, really close to zero. And that number is not that much different than this number, because we have 11 zeros before we get to any numbers. And statistical software usually has default values called the minimization criterion that define when the program is going to stop iterating. Does that touch on your question?
In this example, it seems that the model then fit the.
Yes. That when our loadings are not changing much anymore, which is evidence of that second derivative being very close to zero, we're going to say that the computer program has converged. It has got three numbers that express to you what those loadings are. And that's what's going on. So in the little magic trick above, if I start out with the number 1 and I apply the formulas, I'm going to get three numbers that are all positive numbers because I started the search out at 1. And if I started out at -1, I'm going to get three negative numbers that are identical except for sign. So if you want to think about that, in the first case, given that these are vocabulary scores or intelligence test scores, if you will, the latent variable represents intelligence. But in the case of three negative numbers, the latent variable reflects the opposite of intelligence, or say stupidity, if you want for a better one, or non-verbality, since it's vocabulary. And it's just the interpretation you attach to those loadings. It's because you started out with a given start function, start value. That's why you ended up with the numbers that you did. Is there anything unclear about this?
I have a question. So with these numbers that we stop at three numbers for loading, so are those the location of the point that we saw in the 3D shape, the things at the minimum level? Are those the coordinates of these? Are those numbers the coordinates of this point? Like,
Yeah, right. In other words, the thing is this little graph that I showed gives you an idea what a loss function looks like if I was looking at only 2 parameters. But in this example, I actually have 3 parameters. So yeah, you are kind of thinking about minimizing this in, I guess a 4-dimensional space where you have loading 1, loading 2, and loading 3. And you're taking derivatives to get at the solution, the final set of numbers in 3 space, so to speak.
so I have another question. If I understand it correctly, the first derivative here shows the slope and the second derivative shows how fast the slope change, or is that correct?
Yeah.
So I also remember from our previous math classes, like this in the function, the graph of the, for example, parabolic function, derivative, like it can be like this, derivative shows the area under between the x-axis and the curve. Is this also correct?
Yeah, I think I'm following you, yeah. So
then the derivatives can give different things, like in this situation, it's slope, first derivative, for example, but in the graph, it can also give an area under the axis.
So I'm not quite following.
So the thing, it just reminds me the things that we do in high school. So when we take derivatives, for example, we have a quadratic function and we make a graph of it. And then when we take the derivative, it shows the area between, for example, x-axis and the curve. So if I remembered it correctly. So which means to me, I just want to ask you, the derivative can give different things. For in the quadratic function and graph, it gives the area under the curve, but here it gives the slope.
The integral, right? The integral is the area under the curve, and here we're kind of doing the opposite of that. We're calculating slopes, right?
Oh, okay. So okay,
Yeah, that's good. Connecting the curriculum. Who would have thought? But yeah, that's exactly what we're doing.
So a long time ago, so it's just information pieces in my mind, but I also find a connection. But I think I understand what you say. Thank you.
Right. I mean, the thing about this particular picture is you look at that and you'd say, well, actually, that kind of looks like a parabolic section. But in truth, when you're looking in structural equation models, this surface is not necessarily anything we can know. It is something that we can estimate the properties of by calculating second derivatives. But this is exactly what computer programs are doing when they're starting out with your numbers. You could kind of think of solving this by hit and miss, just guessing the values and making adjustments to things and saying, oh, well, this is really bad, but maybe I'll pick another number over here that's really good. I'll go with this one, and then twiddle around with the values and sort of guess about those things. The other thing about the software that I don't get into this chapter is to say, actually there are many different algorithms to minimize structural equation modeling. And software packages will sometimes change the minimization algorithm based on the number of variables and the number of latent variables in your model. So for example, Proc-Calis inside of SAS will do all kinds of fancy minimization things tailored more to the characteristics of your particular model. Things like Onyx are just doing quasi-Newton minimization. And that's what it does unless you tell it to do otherwise. But the issue here in terms of practically why you care is sometimes you'll start out with a family of numbers And by default, computer programs, some of them like Amos might say, well, I'm going to try to do this to solve your problem, and I'm going to keep going until either I satisfy the minimization criterion or I hit 50 iterations. And if I'm going to 50 iterations, I'm just going to stop. And the answer to your issue there is very frequently you can just say, well, Amos, this particular problem, keep iterating until you do 300 or 400 iterations, and there's no harm in that. So increasing the iterations is an issue. And curiously, that's exactly what I start talking about in here. Just change the iterations. Sometimes when you're running your program, you can have an issue of false convergence. That is, maybe as it's doing its minimization, the search terrain is not smooth. I really should put in a picture, I think, here, but we can come back up here to our little graph. This is an example of a loss function that looks really nice. But say instead of this being a bed sheet suspended over, by 4 points, someone were to take their finger and poke up underneath that and start to give this loss function ridges or folds in it, or ridges, peaks and valleys, as it were. Well, sometimes in the process of minimizing, it will hit a little pocket where, yes, it looks like for this little family of numbers, anything in the immediate neighborhood is a little bit worse. And it'll say, okay, here's my answer, I'm done, when really there exists some other family of numbers that has an even lower loss function. So the terrain can be an issue for you. Sometimes in iterations, you'll have something called false convergence. That is, at some point, the loss function is really, really flat, and the computer program dithers around trying to find numbers that are sort of in that family that are very close. And that has to do with the fact that the second derivative is very close to 0 for that. So generally speaking, if you start seeing messages come back to you about the Hessian and so forth, maybe your model is not well identified in that space. In those cases, usually you find somebody like me and we sit down with your data set and we try to figure out what's going on, because it's usually something that's really close to an empirical non-identification issue. As we pointed out in the little magic example at the beginning, there may be local minima, there may be little minor valleys and hills that are hit, or there might be more than one solution out there that are good. And in those cases, there really isn't a great way to analytically find the global minimum short of doing a whole bunch of start values. So we're getting kind of close to the end of the term, but what I can do is to come back to our little Onyx example. And we're now in a position where we can start to tell you what's going on. So let's show our estimate summary here. And we'll make that bigger. And here's what's going on. Onyx has been generating some random start values and trying to find a minimum solution on this. And it keeps doing it based on that. So these little notes that you see down here on the bottom, let me pause this for a minute, that it has actually solved this factor analysis problem 1,611 times during the time that the class has been running. And it's successfully come to an answer 1,611 times on that. And let me close that script and come back in here. And I can say show all runners and come down here for that. And what you're seeing here are all of the different ways that Onyx is solving your factor analysis model. Down here, these are the least squares values. So we have times that it has solved the solution using the start values, the 1 or -1, and times that it has solved the solution with randomly generated start values. So we'll get into maximum likelihood later, but here's our least squares loss functions. If we are looking at this and you start to see that there's a difference between your user supplied start values and the arbitrary random start values, then you know that it's probably the case that maybe you're looking at a local minimum based on your user supplied start values, and you should consider using the random start values instead. All right, is that okay? So that's, the guts of what's going on. In essence, what this graphical user face is doing is it's taking a given picture, a graphical user interface, and it's writing an OpenMX script and submitting OpenMX scripts to the OpenMX program and retrieving those and organizing it so that you see one picture here and you see the estimate summaries going on. All right, so let's come back and talk a little bit about other techniques. And I give you some of the language of some of the other minimization techniques that are found, and quasi-Newton methods, especially using those, are often, they're not as computer resource intensive. So conceptually, let's now say, well, we understand, or at least we have a walking acquaintance with what least squares loss is. And let's talk about why least squares loss might not be the best thing for you and in fitting parameters to a structural equation model, and why maximum likelihood or generalized least squares might be preferable. So here's something that I've often done in class, and it kind of makes sense to me, and it provokes a class discussion. Consider the fact that I have 4 variables here, and notice that we really captured, we really found a correlation between the first 2 variables. And some of these other variables don't have very high correlations. And we have another large correlation between variables 3 and 4 here. If I do least squares loss, I'm going to get the following predicted correlation matrix out. And if I do maximum likelihood, I'm going to get this predicted correlation matrix. So just from the standpoint of you being a researcher, do you think it's better that you correctly capture the minimum squared error across all of your correlations? Or is it a better thing that we successfully capture some of our correlations at the expense of others of our correlations? This has to be a typo here. I'm pretty sure that's 0.76. Well, my thinking has always been, I don't really care quite so much about capturing these small correlations. And I would really like a model that correctly recovers the high correlations in the data set. So in general, conceptually, maximum likelihood is going to weight the errors of prediction by the magnitude of the association between the variables. Both of these models, maximum likelihood and least squares, are going to be wrong. They're not going to completely capture all the correlations, but maximum likelihood is going to try to do a better job of capturing associations, large magnitude associations in the data, and not worry quite so much about being wrong about the lower associations in the data.
I have a question.
Yeah.
So what if the computer picks the estimator it wants to use? So for example, I try to, I run a model and it uses something like diagonally weighted least square.
Mm-hmm.
Do I force it to use ML?
Well, the fact that you're using diagonally least squares, you're probably using MX or M+.
Yeah, Lavan. Arrow.
And Lavon, okay, but the reason that you're using diagonally least squares is probably because you have categorical dependent variables. That maybe some of the criteria that you are predicting or some of the manifest variables in your factor model are not continuous, but they're categorical. And in the chapter later on where I talk about categorical dependent variables, we talk about diagonally weighted least squares. The thing is, in maximum likelihood, I mean, the estimation techniques in this chapter, we're treating all of our manifest variables as continuous. And that doesn't take into account the fact that when you have categorical data, the estimations of those variances and the associations has to go through something called a link function. So I guess what I'm saying is don't slap the hands of your computer program and say, do ML for me, because in your case, you must have some specification of a categorical data variable that's being predicted to have it go into diagonally weighted least squares.
Okay, thank you.
Okay.
Yeah.
And this is kind of the funny thing about teaching this class is, we do things at different levels, and I can only unpack it kind of in sequence, but we get to this later on. More questions? I mean, it feels like, the issue of minimization and loss functions is a little bit of a heavy lift. So usually this stimulates some questions of, can you say this over again? Or I'm not getting what you said. So what does this loss function look like? Well, what we're going to do is to think about sigma, which is going to be a matrix of predicted cross products. So if you're analyzing a variance covariance matrix, it's going to be a matrix of predicted variances and covariances. If you're in the adjoint matrix, it's going to be a matrix of average sums of squares and cross products. And S is the actual matrix that I have in my data. So it would be my actual variance covariance matrix. And what I have in here is the formula for the loss function. So I'm going to take the natural logarithm of the determinant of the predicted variances and covariances plus And let me read this part in here. This is my actual data set multiplied by the inverse of my predicted variances and covariances. That's going to be a square matrix. And trace is a fancy word for saying I'm going to take the sum of the diagonals of that resulting matrix minus the log of the determinant of the variances and covariances in my data minus m, which is the number of parameters. So, it's a little bit of scary math, but what I want you to observe about this is that every time we do an iteration in our computer program to get at a family of numbers, we're going to have to calculate the determinant of the the predicted variances and covariances. And I'm going to have to take an inverse of the predicted variances and covariances and multiply that by my data. So every single time I have to take these matrices and calculate an inverse and so forth. So computationally, maximum likelihood is going to be more work than least squares loss, where I'm just saying, what's the predicted number, what's the actual number, square it and add it up. And for that reason, it's a little bit more computationally intensive. Now, if I actually nail it, if the predicted variances and covariances are absolutely identical to the other ones, this S times sigma inverse is going to be the inverse of S. So this is going to be an identity matrix. And if sigma completely recaptures, the value of the trace is going to be m, how many manifest variables I have in the data set. So it's helpful now to go back and look at our loss function in matrix form. And this is a matrix analogy, an analog version of that longer version of least squares loss that I wrote out before. And here we see our old friend, the trace. So this is going to be the actual data, the variance covariance matrix, minus the predicted variance covariance matrix squared. And this trace is adding up all of the individual variables. Generalized least squares looks like this. So notice in here, I've got the inverse of the variance covariance matrix in my data, and I have sigma. Well, it's expensive in terms of computer programming to calculate the inverse of this variance covariance matrix in your data every single time you do an iteration. Generalized least squares calculates an inverse of your observed data, and you do that once. So it's not going to be as expensive as maximum likelihood. And for that reason, sometimes if you're having a really huge SEM and you're having trouble getting computer resources, given that computing power has kind of exploded, so maybe this is antique advice, but we would sometimes look at generalized least squares values as a way of getting a family of numbers that we could then put into maximum likelihood later. And that's the point that I mentioned down here. We don't generally use GLS that much, and there are reasons for that we'll talk about in terms of how we get to fit measures in chi-square models. Basically, all of the SEM fit statistics are optimized for a maximum likelihood solution. Much like Anne mentioned, if you look at structural equation modeling software, you can find that there's other loss functions that you can pick. And asymptotic distribution free is an attractive thing for a lot of people. And its loss function looks like this, that I've got I'm going to take my observed variance covariance matrix. I'm going to turn it into a vector, a really skinny, many road column with, sorry, many road single column of data. And in the middle here, I'm going to have a weight function. In theory, this is going to relax the requirement of normality. And for that reason, it was attractive, and a lot of work got done on estimating this weight function. And I give you the technical details here of what that looks like. Generally speaking, this approach does not work well unless you have really large sample sizes. So if you have tens of thousands of people that you're modeling, perhaps asymptotically distribution-free loss functions are worth your while. But for smaller data sets, let's just say less than 1,000, it's not going to be worth it for you to look at. So, my long story short is asymptotically distribution-free loss is a feature of many structural equation modeling software programs. I don't think that it's going to be anything any of us in this class are going to want to be using. Even though ADF loss functions were kind of a failure in practice, the math that went behind it led to something that was somewhat useful. And this gets a little bit to Anne's point, that we can do something called weighted least squares. And sometimes data containing variables that have only discrete values, but represent an underlying continuum. One simple example here might be, Likert questions that are 1, 2, 3, 4, 5. That's not really a continuous variable. And weighted least squares is an approach to estimating what that model is via a link function. And I see I've been talking quite a bit here, and so I'm going to put a pin in it here and take up weighted least squares at the start next time. And then diagonally weighted least squares is the next thing. So we'll get into at least saying what those things are, but the chapter on categorical dependent variables will get into that in more depth. Okay.